Yeah, so the title is taken from this little short paper, but it's so short that actually also going to talk about some other abstract nonsense. Like one thing we have later about, which is kind of a justification for this world, wasn't created the need to do something like that. And the other bit actually traces back to a paper of Prakash and collaborators from 2003, which was like one of the, you could say within the computer science community, the first one which sort of started to seriously think about causal structures in physics and stuff like that. Yeah, anyway. But before that, I'm going to tell a tale about academic terminality. So it's connected to Prakash, but in order to make sense of the story, I have to say something about myself. A lot about myself. So I started a PhD in quantum foundations in Brussels in the 90s. This was like in an area to do with the sort of stuff John Barrett talked about this week in the course. And unlike now, when this kind of hidden variable stuff and all that is kind of quite popular and fancy, at a time in Brussels it was a complete no-go to do stuff. Well, in the world, it was just a complete no-go. There was just no jobs whatsoever in quantum foundations in the 90s. Not one, zero. Just nothing. So this was actually a really bad career choice, and I was badly informed by, say, a supervisor. And because at the time there wasn't really any internet yet, any proper internet yet. So this was no future. Right. So then I kind of moved to Geneva, because there was an old school in quantum logic, sort of stuff Bart talks about now. And well, it looked all very exciting and all that, but basically the field was actually already dead at the time, so obviously there was no future. Then I went back in Brussels, and stuff happened. Some people know about, some others don't. I'm not going to give a lot of details there. But,
don't need details.
Basically, they kicked me out, but with a little bit of blackmail, I got myself a golden handshake. And so I went to explore quantum gravity in London. Then to be told by Chris Isham that none of his students, for I don't know how long, actually got anything like a proper postdoc or whatever. So yeah, right. That and again. Wow, category theory, Montreal. So you give your first talk in the category theory seminar in Montreal, and the most lively person in the room is 85-year-old, whatever, 82-year-old Jim Lambeck. And you kind of all also know pretty much where you are, right? So, okay, new development. Art Institute of Chicago. I actually got a faculty position interview there. I don't know whether you remember that. When I was in Montreal, and Jim Lambeck offered me a suit, but it didn't fit. anyway, I basically got recommended to go to Alcoholics Anonymous because of my act at the post-interview dinner. Right. Back in Montreal, and I actually started my career in engineering and architecture, and I had to do some internship in the summer in some company, and at that moment I decided, this was before I moved to physics and math, I decided I'll never want to do anything with the real world. So I was really desperate to stay in academics, and I was so desperate that I actually considered a PhD in computer science. So
I had nothing to do with the real world.
Well, so I went to somebody there with like a nice friendly face, and I knocked on his door and I said, I want to do a PhD with you. It really happened. Well, you would, Prakash, everybody says he's such a nice person, he would say, obviously, yes. They basically told me to shut up and go away.
Wise move.
It's true. It's true, I'm right.
Not quite in that tone.
He said go away, shut up.
No, anyway, no, actually, basically what he said there is a certain creature in Oxford, he said, and it would be interesting to put you both together in a cage and see what happens. And I didn't know what he says. And the creature is an unfortunate absent of his meaning, which is this guy. Some people know, and some people who have spent some time in a cage, we would know what I'm talking about. Right? So he did like my cigar. Then we scared away along. Okay. You know where this is?
Is this in Barbados?
Gross.
Roots, yes.
In Barbados, yes. Right. Anyway, here we are now, 13 years later, and let's give it a hug. So yeah, so it goes without saying that to a great extent the reason I'm even standing in here is due to Prakash, who basically literally said, you shouldn't do a PhD, you should do a postdoc. And also for the sounds of a brown skill I've never met before, and he has a lot more money than me.
In fact.
That's what he said. And there is this weird guy called Kim Martin, and it would be really interesting to see if we put you together in an office. It was interesting. That's the least I can say. Anyway, okay, let's go to the talk now. So first I'm going to talk a little bit about this paper. Well, no, actually, no, I'll start with the first one. So, there's a lot of stuff people refer to as being causal, and like, one is something called causal structure, and you may have heard Prakash talk about when he gives like tutorials about space-time structure and the axiomatic like composition of different levels, and then sort of reach the person which says from this location in space-time, I can get to this location without violating the speed of light. That's what people call the causal structure. Usually they account for a little bit of topology. Let's see this discrete, and you find this, for example, in Penrose. And more recently, people in physics are getting very excited about the stuff done by Pearl, which also involves causal structure in a very different way. But so it's basically a partial order. Okay. Then there is this thing called no signaling, which we, for example, saw in Samson's talk, and John Barrett talked a lot about this in his talk. He's one of the people actually has been pushing this forward. And the main idea about those non-signaling is if you got some operational theory with devices, with inputs and outputs, you want to account for the first thing, causal structure. That these devices won't allow you to do things faster than light. Then they would violate relativity, right? More recently, some guys came up with something they call a causality action. It's like very recent, like 2010, which is basically the idea of non-signaling from the future. For example, if you do quantum measurement, your outcome shouldn't be used in the past. It's sort of an obvious notion. So these two seem to be clearly distinct, because this is about non-signaling in space. This is really backward non-signaling. This is intended to capture this, but then in a paper Ray Lal and I had like a few years ago in PRL, we observed the following thing. Like if you take causal structure, like as a partial order, then there is a clear notion of time reversal. If in T you got A is below B, then backward time you would have B is below A. Right? It's obvious. And then if in the forward time you can't signal from A to B, then in the backward time there won't be any signaling from B to A. It's sort of non-signaling is preserved under time reversal. It's sort of an obvious thing. Now, this turns out to be not the case for the non-signaling which people use, and as in the operational definition, which should restrict devices. And so we came up with a counterexample. So what you got here is like the sort of stuff Samson's talking about too. You got a matrix, which means you got two parties, A and Bob, Alice and Bob, and if basically this gives all the transitions from say 0, 0, 1, 0, 0, 1, 1, 1 to as inputs to something else. And it doesn't really matter, but this is something which is classically encodable, probabilistic. What I'm giving here is just the relationships, which input can be related to each output. And then if you time reverse this, which is basically taking the transpose, I'm not going to go in details, you can actually a signaling device. If you have a non-signaling device, two inputs, two outputs, you read it backward, you get a signaling device. It's a weird thing. And it clearly is against this idea that non-signaling is reversed, is clearly something which is preserved under time reversal in this sense. So it's kind of a weird thing, something goes wrong. So what is wrong? Well, my claim is what's wrong is basically that this definition of non-signaling, which people use, like John Barrett talked about, Samson talked about, there's something bad about it. And this is something Rob Speckens has been telling to me for years. Like, oh, this definition is wrong. I didn't have a clue why. And basically, what I'm going to talk about in this talk is why is it wrong, or what's bad about it. So what I just talked about was in this paper, like this sort of time reversal thing. Now, it's a very simple argument actually, what I'm going to talk. So basically, the context we will consider is that of a process theory. And a process theory is basically...
Just on the last slide, did you have the right date for that? 1988?
No, that's,
Oh, no, that's not the date.
that's not the date, it's 11.
Ah, shoot.
Missing.
I just thought it was 160.
Yeah, no. So the context I'm going to talk in is that of a process theory. So here you would have like a process with one input, maybe at Alice's side, one input at Bob's side, an output at Bob's side, an output at Alice's side. So that's a process theory. So advertisement, very soon there will be a textbook which actually explains quantum theory and computing quantum foundations purely in terms of these diagrams. But the point of this book is because most people know about categorical quantum mechanics, but you can't solve category theory in physics. And the only reason you actually have to do category theory is because otherwise you can't get your papers except for licks. But you can basically tell all the story about diagrammatic quantum stuff purely in terms of the diagrams without ever mentioning category theory. You can do that. So that's what we've been doing. It just takes a long time, and diagrams take a lot of space and a lot of time to draw. So we expected it would have been published, but it's still not. So it's not even finished. Anyway, so in category theory terms, what we're talking about is strict symmetric monodic category. That's it, if you want to. And so strict symmetric monodic category. And what we call a state would be a process without an input. So this would be a state, something without inputs, only outputs. The dual is an effect, that's a box without an output. And an example of an effect would be discarding. We will use this notation for the idea of discarding some information. You forget about it. And so you got an input, which is your information, and then you forget about it. There's no output. And then you can define something which we call terminality. We say a process theory is terminal if for all processes, if I perform the process and throw away the output, is the same as just throwing away the input and never performing it. It's a very operational, obvious thing. And since this box is not connected to anything else, it's supposed to be isolated from anything relevant, and then you expect this to be true. It's a very simple principle. You can show, well, this is actually equivalent to what this guys which I mentioned before, called the causality axiom, which meant no signaling from the future. You can show that it's literally boils down to such a simple thing. So then you can show a very simple proposition that this picture I just showed before is the same as that all effects that you got in your theory are discarding, because if you got this equation and this thing doesn't have an output, yeah, then this thing has to be equal to that thing. So there's only one effect. And that's the same as saying, yes, so there is only one effect, then it's discarding. And that's of course where the name comes from, because this means that the tensor unit is terminal in your symmetric monodic category. So it's just a short word. And I didn't want to call this like causality axiom, because the word causality is so way overused, right? So at least this is sort of a mathematical connotation. Now, in something like quantum theory, this means that, or like in probability theory, this means that your probabilities are normalized, and up to 1, that's what it would mean, that your states are normalized, that if you got CP maps, that they're traced reversibly, if you're working with like measurements that they form a resolution of the identity, that's all implied by this axiom. That it does all that for you, so in many theories. So it's what people kind of automatically do, normalize. I first called this normalization actually in the first version of this paper. People complain, yeah, but trace preserving is not the same as normalizing. Yeah, whatever. But okay, but the idea is it's normalizing. Okay, now what is non-signaling? Non-signaling for one process, it makes sense to write it down like here. So this is Alice's input, Alice's output, Bob's input, Bob's output. And so the idea is that Alice cannot signal to Bob, so whatever she sticks in here shouldn't be deducible from Bob, for Bob. So, and you can express it by saying that from Bob's perspective, okay, he puts an input in his system, he gets an output, but this should not depend at all on Alice's input, so this is disconnected. So it's as if, from his perspective, Alice's input is just discarded. So that's sort of the natural way, this is the simplest natural way how you can formulate this card. Of course, Alice's output never comes into the game from Bob's perspective. So that's why I discard this here, right? And so it's think a bit about it, that really means non-signaling. From Alice to Bob, and then from Bob to Alice, there was this picture. You know, signaling from Bob to Alice. Now, okay, but so before, I wrote terminology down for a process theory, for an entire theory. So I mean, all boxes should satisfy this. Now I was just talking about a particular process, and then the naive thing you could do, like, oh, let's assume this for all boxes. And then we call this, now we have a non-signaling theory. But that actually doesn't work. It doesn't work because in your symmetric mode category you got stuff like that. So like you just swap two systems. And obviously this is now signaling to there. But you could do this locally. You want this in your theory. You want to have the ability to change locally. And this obviously clearly violates the previous thing. So what you have to do is you need to restrict one way or another to this process without explicit signaling. Like, if two things are potentially separated, then they shouldn't be able to signal. So this is not something which should be allowed to be sort of causally separated, the left from the right. So I'm using the word causality because that's actually what you have to do. You have to sort of consider the internal causal structure of these processes. It's the only way you can do that. And so you want to say, well, if Alice and Bob don't have explicit signaling, so if they're far apart and cannot have signaling, then they should still be able to communicate. Then they shouldn't be able to communicate. And the most general internal causal structure which kind of satisfies this idea is this. You see, I've got Alice here, I've got Bob here. They're allowed to sort of share something from the past. That's okay. Their stuff can come together in the future. That's okay. But there shouldn't be something from Alice to Bob or from Bob to Alice directly. And a theory is non-signaling really is to be understood as something of this form shouldn't be signaling. Something of this, and this, you can see this is the most general thing you can get. You can play around, it's a bit tedious. This is really the most general thing you can get, even internal causal structure. Is that clear? It's really the most general thing you can get. Now, our definition now of non-signaling is that a process theory is non-signaling if everything of this form is non-signaling. That's
Is it n an instance of this thing?
is what? This is actually, so you actually focus here on two space-time events you really care about, like Alice's input-output process, Bob's input-output process.
Right.
So it's a much simpler thing. It's much simpler. I would say it's much simpler. This.
So I'm carrying what those.
I know the
an n like that.
This would be more sophisticated than this, I think. This would be more. This is more complex. Like Tobias Fritz has now done a lot of stuff, like looking at many different causal structures and generalizing these sort of notions. This is the most simple situation. This is like bell type scenario, the simplest you get, like just two parties, and they do an input-output thing. Simplest possible scenario. So anyway, this is now the definition of a non-signaling theory. And the main result is that for every process theory, just from this normalization, terminality conditions, non-signaling automatically follows. You don't have to do any work. It's very simple. Let's prove this. So this is a special case of this action, because there's a unique effect. So on two systems, this would be twice this one, by transfer structure. And so this is a special case. In the case that there are no outputs here, this means that anything with two inputs should be equal to that. Of course. So this immediately, so one part of our diagram immediately trivializes. This immediately trivializes, and we get this. And this is really like a typical bell type scenario. Okay? And now we're going to use this terminality. Now we're going to look at the definition of non-signaling. Signaling says if I take one output, and I sort of kill it, then I should get a decomposition. Then I should get a decomposition in killing the input and a box. And this is very trivial, like we do this goes down, up, this becomes this, and we're done. We're done. So it's no signaling. So that's the key, that's what I was saying is the importance. You can actually prove the converse too, that from non-signaling you get the other one. And that's really trivial, because you just take the second system here to be trivial. So you hide this side, and then this becomes a number, and if you then just ask if there is only one scalar, then this is the identity, so it's trivial. They become trivially equivalent. Now, why do I say this is the secondary result? Let's discuss a bit. Like non-signaling, to even make sense, requires causality. Usually in all treatments people do in the literature, this is informally treated, the causal structure. It's never formally treated, it's informal. But if you want to sort of say what it is in the way I was doing for, say, theory of processes, you have to, otherwise you get nonsense. So in order to even be meaningful, you have to make causal structure explicitly, but then it just follows from this very simple normalization condition. So, which is much simpler, of course. And so yeah, it's both conceptually and mathematically simple. Conceptually, it really means if you got a process and you're going to throw out whatever you get out of it, you can as well not do it and just throw away your input. That's what it says conceptually. So we would say that then this action, which these guys from Pavia call causality action, or no signal from the future, is more fundamental, I would say. And that's on the pages you want to develop a general theory of processes and stuff. Now to go back to this like weird example I had before about time reversal, to understand, well, that was just because we were very confused about it. I know many people were very confused about that example. So causality can be time reversed, but there's just no sense in which processes can be time reversed. So I was actually cheating by giving a relational version. But there's actually no sense processes can be time reversed. The definition of hidden variable theory doesn't really time reverse if you start analyzing it. And this is so obvious from this definition. This is completely asymmetric in time, obviously. It's about effect, this special effect, there's no special state. Yeah. So it's kind of, so anyway, so that's a very simple story. And to show like basically this paper from Prakash, and one of the things they showed is the general covariance result. Covariance means like different observers basically observe physics in relativity theory, and they showed it in a very abstract setting. And you can actually just do this with all the structure I gave you already. That's enough to show covariance, relativistic covariance. I can show this just with this from a simple principle. So what is the idea of so once you get a diagram, you get an idea of a hypersurface evaluation. A hypersurface, like in GR, is like, well, it's some sort of a choice of like what is spatial stuff for a certain observer, what he decides to be. And so an foliation is just a bunch of hypersurfaces which sort of progress in time. And here I make a choice, but like a different observer could decide to do this instead. So this is choice of foliation. Now, once you got such a foliation, you can think about evolution. Like here we got a state of a system, and then, okay, this is the state at a later time, this is an next level, and then at a later time you get maybe this state, later time you get this state. And the idea of covariance, of physics being independent of your observer, means if you look at one of these things, then it should not depend on in which foliation you're actually working, which means for all the different hypersurfaces which go through here, state should be the same, what they see locally. And this is true, like, and exactly by this concept I just told you, this terminality concept. Like, okay, so here we got a thing. So this is the state this guy sees. He doesn't see this. This is somewhere else. So we just trace it out, right? Okay, here we've got another diagram, but by this condition of terminality, this is equal to this. Yeah, this is equal to that. And here is another one, and by the same condition, it's equal to this and it's equal to that. So this very simple terminality condition actually gives you relativistic covariance in a very trivial way. So you don't have to say much. Yeah, okay, that's it. Okay, that's it. Thank you.
This is the first time I'm seeing this proof and I'm trying to connect it to our
It's the same.
proof.
It's the same.
Kind of
It's the same, you don't realize it because you think normalization, when you're just working with states, so normalization, you do unconsciously, but it's normalization which is doing all the work.
I see. This is the thing you just submitted to QPL?
Well, this last thing was already in this old paper with Ray, causal categories. This proof was there, but we didn't at the time even realize the power of this terminality, which is such a simple concept. Like tensor unit is terminal in your categoricals, and you get a lot. You get this no signaling for free. You get it should be based on very axiomatic foundation now, I think. And it was invented by I should actually have put the reference here. It's invented in Pavia by Dariano, Kiribella, Perelon. They start to use that as an axiom. In a completely different context, of course, in reconstructions.
They already used that tensor unit is final? They had that formulation?
No, they didn't know category theories. But they did prove that there is a unique, they said there is a unique deterministic effect. They proved that. And that wasn't a derived thing, that was a derived thing from them.
Because I also used it yesterday in my action.
Yeah? Yeah. So it's really fundamental. It's very simple.
Yes, Phil. Can you go back to that slide where you have an F with two inputs and one of the inputs you
This
answer?
one.
Yes, this one. If F is I'm probably not understanding this correctly, but maybe you can clarify. If F is a control not a C not gate, then I'm assuming you're not saying that you can just obey the control.
See, not gate it violated.
Okay. Well, if you had a
Because
C not gate,
C not gate is highly signaling.
if you had a C not gate that,
A C not gate is highly signaling, so it's supposed to violate this.
yeah,
It's supposed to violate this. And C not gate, and in particular C not gate doesn't have this structure. C not gate does not have this structure.
yeah,
That's the whole point. So
okay.
C not gate is something you want to exclude from your consideration.
Mhm.
Any other questions or comments? Yes, Peter.
Yes, question about the title. Is it could you state it as a two-way implication, fairly reasonable definition?
Oh, it is. I showed.
Yeah.
I showed the. There's a story why it actually ended up being like my initial title was called normalization is equal to or is equivalent to. Do you remember? Normalization is you read it. Normalization equivalent to non-signaling, and so the only condition you need, which I just showed, so this theorem is unique scalar. There's only one process with no inputs and no outputs. That's the additional condition you need for two-way.
Art?
Is there, so your non-signaling condition, can it also be described in the format section F must be of the form G tensor H? Is that equivalent or stronger or weaker? Because if it's of
What is your question? It should be. I can't imagine anything simpler than this, to be honest. Which would
No,
still
but
catch.
certainly if F is of the form G tensor H, then it's
Of course, yeah,
But is
it
it-
doesn't have to be. It doesn't have to be. There are things which are not of that form and are definitely
okay,
not
that was my
signaling.
question.
Like
You have a simple example?
wait. XOR? It's one, I think. XOR is one, I think.
Or swap gate? With just the symmetry of.
No, swap gate is signaling, but XOR is not signaling. I think. But there definitely are such things. Many.
I'm curious.
Like anything you build like as an invariable process. So like I could just build a thing like this. I can build a thing like this with classical probabilities. And then you have an example of something which is not factored. Like what people try to show is an invariable theory really means it implies it's not signaling. So these things are all there.